Hi everyone, good afternoon. Welcome to our webinar about material characterization. I think I have a tiny technical issue and I can't see the webinar slides, so just one moment.
Sorry.
Perfect, now we have the slides and we can actually start. So, good afternoon everybody and welcome to a webinar about material characterization and how it can be used as a tool in product development and reliability engineering projects. My name is Sanna Lahokallio and I work as reliability consultant at Trellick. Before going to the actual topic, I will shortly introduce Trellick and what we do. So Trellick is based in Finland in a city called Tampere, and we help our customers to prevent and solve problems related to reliability and materials. We have specialized in electrical engineering and electronics and to those materials that are used in these industries and their applications. We work a lot with polymer materials and especially their long-term stability, but also other materials such as metals. And as said, we try to help companies to prevent the reliability problems, so already take these things into consideration in the R&D phase, but we also help to solve the reliability issues when those happen after the product launch in the field, for example, by doing failure analysis. And here is an overview of the fields of our services. So we offer both experimental work and consultation as services. And in reliability analysis, we offer pretty much the whole package. So we do test planning, actual testing, both standard testing and tailored testing. Then we designed and built various measurement systems for data logging, and we also do reliability prediction. Then we perform failure analysis for the structures tested in reliability testing, but also for the products which have failed in the field. And then the third topic is the topic of today, material analysis. And there we offer measurements with various analysis methods, and we can also help choose suitable materials. And here our viewpoint is the long-term stability and reliability of the chosen materials. And then in addition to these three main areas, we also offer services in electronic interconnections, mainly with adhesive interconnections and with flexible, stretchable, and wearable applications. And reliability analysis and failure analysis, they were already topics of two earlier webinars. And if you missed those webinars but would like to see them afterwards, you can check them in our YouTube channel called Trellick Ltd. Perfect. Then let's go to the actual agenda of today. So here you can see the outline of this webinar. First, as an introduction, we will discuss what is material characterization, when should it be done, why should it be done. Then we will discuss about different materials, what kind of properties do they have, and what kind of effect environmental conditions have on those properties. After that, we will check some material characterization methods and how they can be used to help in reliability analysis and in R&D. And then in the end, there is a summary. So why should material parameters be measured? First of all, let's define what material characterization means. So it is those processes and methods which are used to analyze and measure composition and properties of material. So basically, it just means how and those methods that we use to measure properties of materials. And those parameters should be measured to actually understand how the materials behave now and in the future. Well, commercially, there is a huge number of different materials available. And usually in any product, it consists of more than just one material. So there is a lot of different materials used in one product. And material characterization can be used to understand how those single materials behave, but also how the combination of materials behave. Then plastics or polymer materials, they are increasingly used to replace other materials, such as metals. But the behavior of plastics is much more complicated than, for example, metals. And material characterization offers a tool to understand how these materials behave. Then, even though there is a huge number of materials available, still materials may limit some functionality or the overall reliability of a product. And with characterization, it's possible to study these limitations beforehand so that there are not going to be any nasty surprises with reliability problems afterwards in the field. And new materials are all the time developed and becoming to the market, which is of course a good thing because then new functionalities can be done. But usually these materials, they have totally new properties and there is no history data available. And that's why, again, if these new materials if their properties are measured beforehand, then this kind of history data can be kind of gained already before actually having any history data. Then when one purchases a material, it usually has a data sheet which tells at least some of the parameters that the material has. But those parameters, they may not be stable. So aging affects the parameters. Aging can just happen due to time. And then also different environments, they have an effect on the parameters. Processing can affect, and so on. And again, with characterization, this kind of stability changes can be studied already beforehand. And as I said, the datasheets are usually provided from the material manufacturer, but these may be incomplete for your own needs. So they may not state some certain parameter that is important for you. And sometimes there are even mistakes in the datasheets. And one more thing where characterization can be used as a tool is quality control. Because similar materials, they may have very different properties. So for example, all epoxy materials or all polyurethanes, they are not the same material. They can have very different properties, even though they have the same name. And we have quite often been involved in such a project where at some point in the supply chain, a subcontractor has changed material to similar, but usually cheaper one. But then this new material has totally different properties and then failure starts to occur. So with quality control, if the materials are regularly measured, then these kinds of changes in the parameters, they can be found already before the materials end up in the actual products. Then let's talk about materials. So materials can be divided into three main groups, which are metals, ceramics, and polymers. And when at least two of these main groups are mixed together, then a composite can be formed. And of course, within each of these main groups, there are a lot of different materials and they have different properties. So metals are not the same, all ceramic materials are not the same. But then if we take just the characteristics, properties of each group, we can a bit compare the different groups. But of course, all of these parameters stated here are not valid for all of the materials belonging to certain group. But in general, metals have high electrical and thermal conductivity. They are very malleable, easy to process, ductile, but also hard and usually pretty heavy. Metals are often used as alloys, so mixture of metals, for example, materials like brass, but also, for example, solders, which are used to attach components to printed circuit boards. Then if we consider ceramics, they have excellent thermal properties. They are very stable in many environments, very good resistivity to chemicals, for example. Mostly they are dielectric materials. They are hard and rigid, but also brittle, so they break easily. And technical ceramics that are often used in industrial products tend to be expensive. Then there are plastic and polymer materials, which are used to replace the latter two materials. And that's because they have very light weight and low price. And plastics are also very easy to manufacture. But on the other hand, they have poor thermal properties and they absorb moisture and solvents. And their properties especially tend to be unstable. So environmental conditions and long-term exposure alters their properties. And especially with plastics, it's good to bear in mind that the same name refers to many different materials. So all epoxies are not the same. Then when two or more materials are combined to form a new material, then a composite can be formed. Composites has properties that none of the mixed parts have separately. And those materials in composites, they stay separate. So composite is not an alloy. Those different materials, they can be identified. As an example, there is a picture of a printed circuit board where you can see metals as vias and traces. And then the board itself is formed of polymer material, which has been reinforced with ceramic material. And characterization of composites can be challenging and require some expertise because the materials affect each other's. Here is one kind of quick overview how these material groups can be compared. We can take, for example, thermal expansion as an example. So the thermal expansion of ceramics is pretty small. For metals, it is already a bit larger. And for polymers, it is much larger compared, again, to metals. So it increases. Then let's check what kind of effect environmental conditions can have on material properties. Generally, the environment may significantly affect the properties of materials. And these kind of typical environments that affect are, for example, temperature, humidity, chemical exposure, impurities, corrosive environment, and so on. And as said already beforehand, materials age and their properties are not stable. And this can, of course, significantly affect the functionality of a product where these materials are used. First, let's talk about temperature and especially high temperature. Of course, other temperatures can also have an effect. For some materials, low temperatures can be harmful, and quite often cyclic change of temperature between high and low is harmful, for example, for electronics. But here, let's take the effect of high temperature as an example. So high temperature may change many properties. It increases the rate of chemical reactions. It impairs mechanical properties and changes electrical properties and affects chemical resistance. There are two examples on this slide. Let's first talk about the relative change in Young's modulus. So how this effect of high temperature impairs mechanical properties. This picture here on the upper right corner. So Young's modulus describes the stiffness of a material, and here it is measured as a function of temperature for 4 different materials, for 2 epoxies and 2 silicone materials, which are all used as an adhesive. And as you can see, when the temperature increases, also the Young's modulus decreases, but it depends on the material how harsh the change is. And for example, for this blue material, which is the snap cure epoxy, there is a huge drop in the Young's modulus around room temperature. So if we need a material that should be used at room temperature, we should not choose this blue material because it's not stable at this. It's not stable at this area. And why there is such a big drop is because this material has its glass transition at this temperature. So glass transition means a temperature area where solid material becomes more soft and rubbery-like. And there is a big change in the mechanical properties. And for example, coefficient of thermal expansion rapidly increases above Tg. Then there is another example of electrical properties for 4 different polymers here on the lower corner. And this is also plotted as a function of temperature. And as can be seen, the dielectric constant changes when temperature changes, but the effect depends on the material. So if something is measured for one material, the result might be totally different for another material. Some of these changes that high temperature causes, they are reversible changes. So when the product or the material is brought back to room temperature, for example, the changes will disappear. But high temperature can also cause permanent changes in the properties of materials. For example, for metals, it can change the crystal structure. There is an example of this in the next slide. And it can also oxidize materials. Then temperature accelerates chemical reactions, electromigration, diffusion. And when it's combined with mechanical stress, then it causes and accelerates stress relaxation, creep, and fatigue. And stress relaxation is valid for polymer materials. So those relieve stress under constant strain to get rid of the internal stresses that are in the material. And creep and fatigue, they are valid also for other materials. And creep is occurring under static load and fatigue under cyclic load. Here is the example of how the crystal structure of metals can change. So here's it's an example about solder material. So when a component is soldered to printed circuit board using a solder, then there is this kind of thin intermetallic layer or IMC layer is formed in the interface between the solder and the soldered surface. And the IMC layer should be thin because it's very fragile and brittle. So the interconnection breaks very easily at this spot. But due to high temperature aging, this IMC layer can grow. And then, of course, when the crystal structure of the IMC layer changes, then the mechanical properties change and it can break very easily. Here is another example. This is of how the adhesion strength can drop as a function of temperature. So adhesion strength means the strength, how two surfaces that have been adhered to each other, how strongly they are together. And this kind of thing is valid, for example, for coatings and adhesives and over mold materials. And here is an example of a display module, which has been tested in cyclic testing between -40 and +125 degrees C. For a very long time, 10,000 cycles, because the lifetime for this product was pretty long. And as can be seen, there is pretty quickly after the temperature test has been started, there is an initial drop in the peel strength, in the adhesion strength, but then when the aging is continued, the change gets kind of smaller. So it's not changing that quickly anymore, at least for a few thousands of cycles. And then another thing that happens and affects is absorption of moisture. This is not valid for metals and ceramics because they do not absorb moisture in their structures, but polymers, they can absorb very considerable amounts of moisture and water. And when they absorb moisture, it affects many properties, and some of these are reversible changes, but some are also irreversible, so changes that do not go away anymore. When the moisture is getting absorbed, it can act as a plasticizer, which means that the material, the polymer, becomes softer, more ductile. Then moisture can also cause swelling of the material, so its dimensions will change. Then moisture affects the electrical properties. Quite often it is a negative, the effect seen. There is a picture example of this one. So dielectric constant increases when aging in high humidity test increases. Then glass transition temperature, that tends to lower, and also mechanical properties, they decrease. And sometimes when these changes are irreversible, then there are usually some chemical changes happening. So moisture can break the polymer chains and crack the sample. Here is an example of polyester and copolymer, which have been tensile tested as a dry material and wet material. And let's first talk about polyester material. So as if you compare the blue dry sample and the red wet sample, we can see the plasticizer effect. So the polyester material can be pulled for a much longer time. And that's why the strain value increases before the material breaks. Also, the maximum stress decreases a little bit for the wet sample. But then for another material, copolymer material, which is a mixture of two different polymer materials, for this one, the plasticizer effect cannot be seen. So there is not that much difference in the strain values for this material. But also here, the maximum stress decreases a little bit. Then impurities and corrosion is also one thing that affects the properties. And impurities, they are very common. For example, salt is present in many areas, in coastal areas, in maritime applications. Also during wintertime, quite many roads are being salted to prevent ice. Then there is air pollution. Industrial environments tend to be pretty nasty ones. They have, for example, dust and grease in them. And then also organic solvents such as cleaning detergents can cause impurities. And these impurities, they may affect the properties of material, and sometimes they can even cause this kind of irreversible degradation for the materials. And we usually talk about corrosion when humidity and impurities are both present, but also other conditions may cause corrosion, for example, mechanical wear or high temperature. And corrosion is valid for metals and polymers especially, even though when corrosion happens for polymers, people usually talk about oxidation instead of corrosion, but still the phenomenon is pretty much the same. Here is an example for printed circuit boards. These boards have different surface finishes. So there is ENIC, which is nickel gold. Then there is immersion silver, immersion tin, and hassle is a solder coating. And these have been tested for 6 weeks in mixed flowing gas test, which is using four corrosive gases to test corrosion. And as you can see, each of these materials have some corrosion visible on their surfaces. And electrically, when these were measured, especially the enic structure with nickel gold had a lot of failed structures. Here it's good to note that silver is vulnerable to certain levels of sulfur. So if there is sulfur present, then silver might not be the best surface finish material. Here is another example of a phenomenon called environmental stress cracking, or ESC. And this is valid for polymer materials. And they break quickly when there is tensile stress and solvent exposed at the same time to the plastic material. And this is a very common cause for failures of polymer materials. And it's also very rapid and interesting failure, because usually polymers have very ductile behavior, and if they crack, they crack very slowly and in a ductile way. But this ESC causes brittle fractures. And basically this phenomenon, it works so that the solvent and mechanical stress needs to be there at the same time. But the solvent itself, it does not cause any molecular degradation. But the solvent is able to penetrate into the polymer and interfere with the polymer change when the tensile or when this mechanical stress is there at the same time. And this causes this kind of interesting cracks where you can still see this kind of tiny hairs which are connected. And it's good to remember here that internal or the stresses that are needed for this failure to occur, it can be just some internal stresses, for example, resulting from injection molding of a casing, where there is usually some corners with internal stresses remaining. And then the solvent can be, for example, a cleaning detergent if some casing, for example, is cleaned regularly, then this kind of failure can occur. Then let's talk about material characterization methods. So as I have probably already said, the properties within each material group, they vary a lot. So if something is measured for one epoxy material, the result may not be valid for another similar material. Also, a good thing to remember is that properties follow usually a distribution, so they are not a single values, but an area. An example here is the class transition, or TG, of a material, which is usually in a datasheet given as a single point, but it's an area, temperature area. And for example, here, the class transition temperature is determined so that we can give it the starting point, or it can be given as a middle point or the end point. And when usually datasheets just gives one temperature, it would be good to know which temperature it is from this temperature area. So it would be good to know how the properties have been measured and how they have been determined. For material characterization, processing and thermal history may be critical for the material parameters. So thermal history is something that the material has due to the storage conditions and the processing conditions. And this is valid especially for thermal analysis methods. So sometimes we want to get rid of the thermal history if we want to measure if the material itself has some irreversible changes. Then we have to make more measurements for the same sample to get rid of the thermal history and to study the actual material. But then, of course, if we want to study how, for example, a storage condition has been affected the material, then we want to study what the thermal history is. Often sample preparation is also critical so that we can get reliable results. For example, for material characterization, usually just a very tiny piece is needed to perform the analysis. And it's usually cutted from a bulk material. So first of all, it's important that during the cutting, we do not cause any cracks or other mechanical changes to the material. And also it's important that the chosen tiny piece represents well the whole bulk material. And usually also the conditions where the characterization is done, that can be very important. So it changes the properties if we change the temperature rate, for example, by which the measurement is done. There is a huge amount of different material characterization methods available. We don't have time to talk about all of them, so I have divided the methods here to certain groups, and I give you some examples of them. So one possible way to divide the characterization methods is to thermal, mechanical, chemical, and optical analysis methods. And the method should be chosen according to the material and what are the critical parameters for each applications and materials. First, let's talk about the thermal analysis methods. These are used to study temperature-related parameters of materials, and these methods are especially popular with polymers. The widely used methods include, for example, DSC, TGA, TMA, and DMA. DSC, differential scanning colorimetry, is a standard method that can be found in almost every laboratory. It can be used, for example, to measure melting points or class transitions. Then with TGA, weight losses as a function of temperature can be measured. There is an example of this one in the upper right corner, where we have studied the stability of 4 different printed circuit board materials. Then with TMA, coefficient of thermal expansion, for example, can be measured. And with DMA, the mechanical properties can be measured better than with the other methods. When choosing the method, it can be sometimes a bit tricky because same parameters can be measured with several techniques. For example, class transition can be measured with DSC, TMA, and DMA. And the determined parameters with thermal analysis, they usually are not exact. So more than one measurement should usually be done. The parameters depend on the technique used, who has determined the results, who have been using the equipment, what kind of equipment is used, and so on. And there is an example of this one here on the lower corner. This is a measurement done with dynamic mechanical analysis, and class transition temperature can be determined from all these 3 curves that we have here. And if we determine it from the green curve, it is the tangent. And for the blue and red curves, it is the peak point. And determining the TG from each of these curves would be perfectly fine and correct. But the determined value is pretty different if we determine it from the green curve, then it would be 125 degrees C. But then if we determine from the blue curve, it would be 150 degrees C. So there is quite a big difference, and this is the reason why it should be good to know what is the determination principle and what is the equipment that is used to measure a certain parameter. Here is an example of how these thermal analysis methods can be used in real life. So in this case, our customer needed a overmolding material for their electrical device, and the operating temperature for this device was 65 degrees C. And as in pretty many products, also in this one there were various materials used in the device. And as we learned from this table earlier, there is differences in coefficient of thermal expansion values for each material. And when there are these CTE differences, they create stresses in the structure. And that's why the CTE value should be as low as possible and at least as close as possible to each other. In this case, the overmold material chosen only gave one CTE value, which was pretty low and nice sounding value. But we wanted to measure a bit more how the material behaved. And that's why we made a CTE measurement with TMA. And in this case, it was a modulated run because the material was filled. But basically, the interesting curve here is the green one. And the CTE can be determined as a slope value. And when the slope changes here around 50 degrees C, there is the class transition of the material. And as can be noted here, the low value that was stated in the datasheet, it is valid only below TG. And above TG, the CTE increases rapidly. In this case, it is probably 3 or 4 times higher than the CTE value below TG. And as for this electrical device, we needed operating temperature which was above TG, so above this 50 degrees C here. This material is not a suitable material because the CTE value that is stated in the datasheet, it's not valid at this high temperature. And this is a good point why those materials should be tested, and how datasheets may not always give all the properties that are important for your own needs. Then mechanical analysis methods. There are several standard techniques available. These are often pretty easy and quick to perform. Common methods are, for example, tensile testing, compression testing, shear and flexure testing, impact testing, and hardness testing. And then if a dynamic testing is used, then also fatigue and creep can be measured. Here is an example. This is the same example that we already had earlier about polyester being tensile tested as a dry and wet sample. And I just wanted to have this here again so that we can quickly check what kind of properties can be analyzed from this stress-strain picture that we have here. So quite often the Young's modulus is determined. That was describing the stiffness of the material, and that's determined from the elastic part of the curve. And then quite often the ultimate tensile strength, so the maximum stress value, is determined, and then also the elongation at break, which means the strain value at which the material breaks. Then chemical analysis methods are used to study how light and radiation interacts with matter. And these analysis methods can be used to determine chemical composition, how composition varies, to study crystal structures, and so on. And there are a lot of different methods available. Here are just a few examples mentioned. EDX is usually used together with scanning electron microscope, for example, in failure analysis, to study the elements. So it can be used to recognize elements. Then there are a lot of different spectroscopy methods that can be used to study, for example, the composition or stability. Here is an example of FTIR, which basically gives characteristic peaks for each functional groups. And in the picture, there is a printed circuit board material which has been aged at pretty high temperature. And here we can see that the lowest curve is the non-aged material. And we can see that when the materials aged, these characteristic peaks, they disappear, which describes how the chemical composition is getting kind of broken. Then there is still optical analysis, which is used to study surfaces and subsurfaces of structures. This can be done with optical microscopy, with scanning electron microscopy, which is pretty often used in failure analysis. And then there are, of course, other more complicated and more fancier microscopy methods, such as TEM, available. Here is an example of chemical and optical analysis together. So in this case, we were making failure analysis for an attachment on polyimide substrate, which was tested at high temperature. That's why the whole interconnection here is totally corroded or oxidized. But what is interesting here is the substrate material, or the printed circuit board material, which consisted of 2 polyimide films, which were connected together with a thick adhesive layer. And a cross-section was done with this one, and we studied it with SEM. And we were wondering what are these white spots seen in the adhesive layer. And elemental analysis was done using EDX, and we were able to recognize that it was antimony in the structure, which is used as a flame retardant material in the flexible printed circuit boards. Then a few words about material characterization as a tool. There were already quite many examples about this one earlier, but to combine this a bit, we can use it in material selection. So with material characterization, we can compare suitability of a material for an application, and, for example, compare several materials and choose the one that has the best functionality. And when the materials are characterized during the design phase, then the behavior can be learned already beforehand, and those potential failures can be prevented before product launch. And the datasheets may be incomplete for your own needs, so it would be good to know how the analysis is done, which methods are used, at which temperature the measurements have been done. And for plastic, if it's a plastic that has glass transition temperature, is it given there? Is the coefficient of thermal expansion given only below, or is it also given above TG? And so on. These kind of things are important to notice. Then material characterization can be used in failure analysis. So it helps to analyze how materials affect the formation of failures, or it can be used to eliminate reasons for failures, that it's not due to this material, for example. And then long-term stability of materials can be studied with material characterization. So in this case, the characterization methods are combined with aging or environmental testing. For example, the material is aged in humidity testing or high temperature testing, and then characterized after certain time periods to learn how the material functions, because the datasheets usually only give how the material properties are now, but not how they are after 5 years or 10 years in field. And this aging the materials before material characterization can give vital information for reliability and failure analysis also. Then if we choose to study the material, this stability with aging, then there are a few things to consider. First of all, it's usually good to measure something in real time, in situ, to actually know how the samples behave in a certain environment. But with material characterization, it's often quite difficult to measure something in real time. But if it's possible, then let's definitely go for it. If it's not possible, then usually we need to age the sample and then remove samples out from the aging testing after certain time periods, and then do the characterization for those ones, and then kind of with these time periods, we can build the timeline, how the properties change. Usually, the material parameters first change quickly, and then the change gets slower. But this is not often the case. So it's very difficult to say how often you should remove the samples. It's also possible if there is a degradation process, then opposite behavior is caused. For example, after the degradation starts to occur, there is a quick drop in properties, and after that, nothing happens anymore. Usually, if something is aged, we want to accelerate it. For example, if we want to know how the material behaves in 5 years, there's usually not time to wait for 5 years. So that's why the aging should be accelerated by using higher stresses, for example, than faced in real world. But then it's very important to consider what kind of conditions can be used for aging, so that we do not go above the operational limits of the material, because too harsh aging may cause the kind of failures or degradation mechanisms that are not valid for the material in its use conditions. Then there are a few examples I have here. I will go through them quickly because we have used almost all of our time. First of all, here is a stability analysis for polypropylene material. So this material was needed to use in very harsh environment for a long time, and we wanted to know that, or wanted to be sure that it would be stable for a long time. So that's why the samples were tested in 85-85 test, which is a high humidity test having a temperature of 85 degrees C and a relative humidity of 85%. And the aging was conducted for 2,000 hours. And we used different techniques to confirm the stability. First of all, DSC was used, and here you can see, for example, they determined melting temperature and crystallinity, and you can see that the material remains very stable. Also, we studied mechanical properties of the materials, and no big changes were happening there too. So material characterization can also be used to prove that something is stable. Then there is another example of 85-85 test. In this case, it was done for this kind of casing material made of ABS PC, high impact engineering thermoplastic material used as a casing. And here the testing caused deformation and brittlement of the casing, so it cracked and deformed. And the material was studied with DSC, and we noticed that the class transition temperature decreases. So usually it's not good to age material above class transition. That's one operational limit for some materials. And when the testing was started, the TG was above 100 degrees C, so it was above the aging temperature. But then after 1,000 hours of aging, the class transition had to drop below 85 degrees C. One thing that happened in the previous example also was hydrolysis, which is a valid degradation method for polymers which have ester groups in their structures. Basically, when this hydrolysis happens, when we are above the class transition temperature of the material and the relative humidity level is high. And this hydrolysis phenomenon, it leads to breaking of the polymer change, and that's why the polymer cracks. And this happens very often if certain polyester materials are tested in 85-85 testing. Here is also one quick hydrolysis example for polyester. So basically, this blue curve here is the stress strain curve for non-aged material. Then after 500 hours, we can see the plasticizer effect. So we can do the tensile testing for a longer time. But then after 1,000 hours, the hydrolysis starts to affect the material, becomes very brittle, and that's why the maximum maximum stress value decreases and also the strain value decreases. And here is again one 85-85 example for, or polyester example. In this case, we used 85-85 test, but also 2 other tests. So 65-90, which was below the TG of the polyester material, and then also 85-85 testing so that it was cycled. And what can be seen here, that the hydrolysis affects in 85-85 test so quickly that after 500 hours for this display module, we could not do any peel testing anymore. Then if the humidity, or if the humidity level remains pretty much the same, but the temperature is dropped below the TG, then the peel testing can be done up until 5,000 testing hours, and there is not that much drop in the peel strength. And also if the 85-85 is cycled, in that case the hydrolysis happens much slower, because due to the cycling the material is exposed to 85 degrees C, so much less time. Then I will skip this example. It was not that interesting. You didn't miss anything, but we are running out of time, so let's go to the summary. So the changes in material properties, they can cause many different failures in products. That's why it's good to measure, to characterize the materials that can be used to analyze how the materials behave in different conditions. And this can help to prevent and understand failure mechanism and their reasons. It's good to remember that material parameters are not constant. Processing affects, their use history affects the environments where they are used, aging, all of those, they change the properties of materials. And when material characterization is combined with aging, then long-term behavior of materials can be analyzed. And this can be used to prevent failures already during the R&D and to understand failures from the field. It works for both of these. And datasheets and salesmen cannot always be trusted. Datasheets tend to lack the information, especially on long-term stability, and always they do not have all the information that is important for you. Thank you for your interest, and I'm very sorry that I exceeded my time with a couple of minutes. Here you can see the contact information and also the YouTube channel's name if you want to check the previous webinars that we have had. Thank you so much. Bye-bye.